free fall under gravity in the absence of air resistance. All objects fall with the same uniform acceleration due to gravity. And the acceleration due to gravity, A, is written as g, which is equal to 9.81 meter per second square. Notice that the acceleration due to gravity, g, is independent of the mass. When the object falls under gravity, we say its acceleration due to gravity is g, which is equal to 9.81 meter per second square, means that its velocities will increase by 9.81 meter per second. The three equations of motions can still be applied in free falling motion, because during free falling, the accelerations of the body is uniform. Consider a body released from rest, and we take downward as positive. That means the body, the initial velocity is u equal to 0, and it moves downward with uniform acceleration g equal to 9.81 meter per second square. In this case, the equation of motion will be rewritten as v equal to u plus gt, and v square equal to u square plus 2gs, and s equal to ut plus half gt square. For the AT graph, it would be constants with a equal to 9.81 meter per second square, and for the VT graph, it will be a straight line with positive slope, with the slope equal to 9.81 meter per second square. For the ST graph, it will be a curve with increasing slope. If we consider a body being projected vertically upwards with an initial velocity u, and we take upwards as positive, for the AT graph, we have the acceleration of the body equal to negative g, which is negative 9.81 meter per second square. Therefore, it is a straight line with constant value. Since the slope of VT graph represents acceleration, therefore we have a negative slope with constant value for the VT graph, and the slope equal to negative g, and the v-intercept represents the initial velocity. Again, we consider a body being projected vertically upward, but in this case, if we take downward as positive, then we have the acceleration of the body equal to g, which is equal to 9.81 meter per second square. Hence, the AT graph will be a straight line with constant value 9.81. Since the slope of VT graph represents acceleration, we have a straight line graph with positive slope, with the slope equal to g. Again, the v-intercept represents the initial velocity, which is negative value because it's being projected upward, and we take downward as positive. Case 1. Let's consider a ball released. It falls vertically downward and rebounds to the same height after hitting the ground. If we take downwards as positive, then the equation of motion during free falling is V equal to U plus GT, V square equal to U square plus 2GS, and S equal to UT plus half GT square. From A to B, its VT graph is a straight line with slope equal to G. From C to D and D to E, the VT graph is also a straight line with slope equal to G, which is parallel to the original one. From C to E and E to F, the VT graph is again a straight line with slope equal to G. Notice that the area inside the region 1, 2, 3, 4 equals to the maximum height h of the bodies from the ground. When the ball is moving in air, no matter it is moving upward or downward, the acceleration is always equal to g, which is a constant value, except during the time interval, which is very small, when the ball hitting the ground at B, D, and F, the acceleration changes from g to a negative values. Hence, the resultant AT graph has the shape like this one. Since the slope of ST graph represents the velocity v, therefore the ST graph has the shape like this one. With the position of the ball shown, A, B, C, D, E, F. However, if the ball is released and it falls vertically and rebounds to a smaller height after hitting the ground, again, if we take downward as positive, the VT graph will look like something like this one. The slope of these straight lines will be the same, which represent the acceleration due to gravity g. The positions of the ball is A, B, C, D, E, F. In this case, the area under the graph 1, 2, 3, 4 are decreasing. That is A1 larger than A2, larger than A3, larger than A4, because the height of the ball decreases after each rebounds. H1 larger than H2, larger than H3, larger than H4, etc. And the corresponding ST graph will be like this one. The equation of motions becomes V equal to U plus GT, V square equal to U square plus 2GS, S equal to UT plus half GT square. For case 2, in this case the ball is released. Again, it falls vertically and rebounds to the same height after hitting the ground. But now we take upward as positive. Hence, the VT graph will be like this one. Notice that the slope of this straight line are the same. If now, when the ball is released, it falls vertically and rebounds to a smaller height after hitting the ground. Again, we take upward as positive. During free falling, the accelerations equal to negative g, except during rebounds. Therefore, the AT graph will look like this one. And the ST graph will look like and the corresponding VT graph will be and the positions of the ball is A, B, C, D, E, F, G. Again, the area under the graph 1, 2, 3, 4 are decreasing, with A1 larger than A2, larger than A3, larger than A4, since the maximum height during each rebound decreases. That is H1 larger than H2, larger than H3, larger than H4. Lastly, the equation of motions becomes V equal to U minus GT, V square equal to U square minus 2GS, S equal to UT minus half GT square. This equation still can be applied when the ball is moving in air.